Good evening guys, good evening everyone, good evening. I welcome you all again to the NEET Elite after 2 days, yeah? Is that? Hope you guys are doing great, having the good time. Well, let me know in the chat box if I'm audible and visible to everyone right here. Let me know in the chat box if I'm audible and visible to every single guy right here. I'm doing great guys, I'm doing great. Well, people, from past 2 days I couldn't take the session on this channel because I was busy solving the JEE question papers on the JEE channel. Yeah, okay, that's why I was not able to come over here. But from now onwards, these are going to be regular sessions right here. Yeah. Okay, Priya, I'm doing wonderful. How are you doing? How are you doing? Let me know. Good evening, Kelvin. Hi, Pranish. Chetan, atomic structure will do also. Well, Yashwant has come up with the quote, character cannot be developed in ease and quiet. Only through experience of trial and suffering can the soul be strengthened. Okay, ambition, inspire, and the success. That's wonderful, bro. That's great. Okay, well, people, I think in the last session, we did the inductive effect. I hope you remember that. Yes? Okay. Well, in the tonight's session, what we are going to do is we are going to talk about the resonance and the resonance effect in detail, okay? We are going to talk about what this resonance is all about, okay? What this resonance effect is. But let me tell you, this resonance effect cannot be finished in a single session. So after this, there will be one more session on this resonance effect over here and the questions which we'll be doing in the next session, yeah? Right? Okay. Well, before starting the session, let me introduce myself. As you all must be knowing now, my name is Wassim Sir and I'm your chemistry master teacher right here. Okay? Alright, for the ones who have no idea about the NEET 2021 crash course, which we have started on the actual Vedantu platform, well, people, what all benefits you guys are going to get if you'll enroll yourself in this NEET 2021 crash course? People, first thing, you are going to get trained by the teachers of your choice in your physics, chemistry as well as biology. Apart from that, we are going to cover your whole syllabus before the NEET 2021 examination, right? There is no need to worry about the test series, no need to worry about the mock tests. Everything is included right here in this crash course. And at the same time, you'll be getting the separate sessions by means of which you'll be getting to know how to solve the questions in lesser time, about the time management. Everything will be done in this crash course. Everything is included right here in this crash course. And at the same time, it's going to be a two-way learning interactive platform wherein you can ask your doubts anytime to your master teachers, right? Okay. Well, people, how to get enrolled in this, how to take this crash course. You just need to click on the Vedantu app. After clicking on the Vedantu app, you need to click on the NEET crash course. After clicking on the NEET crash course, what you guys are supposed to do is just use the coupon code as WSCC if you want me to personally train you for the NEET 2021 in chemistry, right? Okay, and after using this coupon code, you'll be getting the additional 20% off, and after the 20% off, you are just getting this crash course for 8K, yeah? Okay, well, there is the link in the description box of the video as well. You can enroll yourself in from there as well. Okay, there's a link. You need to click on that link, use the code, get enrolled from there as well. Okay, either you click on the Vedantu app or you can click on the link which is there in the description box of the video. Yes. Kanaya, I'm doing wonderful. Hi, Anthony. Good evening. Good evening. Rumel, chemical kinetics is completed, I guess, or there was one session pending. That was Arrhenius equation, I guess. I don't remember exactly. I'll let you know. I'll check it out. Yeah. Oh, it's not updated in the playlist. All right. I'll talk to the team. They'll do that. They'll do that. Okay. All right. So for the ones who have not liked the video yet, do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? Okay, so let me know in the chat box if you guys are super duper excited for the tonight's session, which is going to be the resonance effect. Yes, let me know in the chat box with the thumbs ups. Let me see the josh of the session first, then we'll see it. Yeah, Then we'll start. Let me know in the chat box. Let me know in the chat box. Let me know in the chat box. Yashwant, he is doing good now. He's doing good. Okay, people are super duper excited. Yes. No, Harish, definitely, bro. We'll be covering everything, organic, inorganic, everything. Physical is almost dusted, right? Yeah. Yes. Hanji, I'm done with the dinner as well. Yes, absolutely. It's 11 right now, 11:10. Okay, so people, let's get to know something called as resonance right here. Okay, first thing, why this concept of resonance was given. Let me make you understand why this concept of resonance was given. Then only we'll get to know what this resonance is all about. And I want you guys to take a note of everything, whatever will be drawing on the screen, whatever I'll be writing on the screen, I want you guys to take a note of every single thing right here, okay? Ashish, bro, this is the English channel. I'm not supposed to talk in Hindi, so yeah. I'm really sorry, bro. This is particularly for the ones who cannot understand Hindi, yeah? Okay? Alright, so what I was telling right here is, what was the need to give the concept of resonance? Yes. Remember guys, whenever we cannot draw the true structure of the molecule, whenever we cannot draw the true structure of the molecule, or whenever a single structure of a molecule cannot explain all the properties of it, okay? Whenever we cannot draw the true structure of the molecule, or I can say something like this, whenever a single structure of a molecule cannot explain all the properties of the molecule, that actually means that molecule will be exhibiting resonance, okay? Got it? Whenever we cannot draw the true structure of the molecule, whenever a single structure of the molecule cannot explain all the properties of it, remember at that time a molecule exhibits resonance. Yes, point number one, right? Which I've told you right here, okay? Now people, if we talk about benzene, right? If we talk about benzene, if I'll ask you what is the structure of benzene, most of you people will give me either this as the structure of benzene, or they'll be giving me this one as the structure of benzene. They'll be giving me this one as the structure of benzene, right? Some people will say this is the structure of benzene, some people will say this is the structure of benzene, right? But people, if you would have studied benzene carefully, we know in case of benzene, all the bond lengths are identical. We know in case of benzene, all the bond lengths are identical, right? All the bond lengths are identical, correct? And one more thing about benzene, benzene does not show the properties of the alkene. Okay, let's not talk about that first. Let's talk about this single thing right here first. Okay, see, if I talk about benzene right here, we know in case of benzene, all the bond lengths are identical. They are equal, right? And what we have drawn right here, we have drawn two structures of benzene. Some people among you have said this is the structure of benzene. Some people among you have said this is the structure of benzene, right? But we know in case of benzene, all the bond lengths are equal, right? If I'll consider this structure right here, as per this structure, between these two carbon atoms, right here there is a single bond. Between these two carbon atoms, right here there is a double bond. Between these two carbon atoms, again single bond, again double bond, right? And we know strength of the double bond is greater than the strength of the single bond. We know that, right? So definitely bond length in case of double bond should be less than the bond length in case of a single bond, right? So as per this structure, will all the bond lengths be same? No way, right? But we know in case of what? But we know in case of benzene, all the bond lengths are same, right? But as per this structure, all the bond lengths are not same. Similarly, as per this structure, all the bond lengths are not same right here. Okay, I hope you got it what I said, correct? See, what I said right here, for benzene, we know all the carbon-carbon bond lengths are identical, right? And benzene, it does not behave like a normal alkene. It does not behave, actually benzene does not behave like a normal alkene, I must say, yeah? But people, as I told you a few minutes back, if I'll ask you what is the structure of benzene, some people among you will be giving me one structure, some people among you will give me other structure, and those structure won't be explaining all the properties of the benzene, right? Those structures won't be explaining all the properties of the benzene, right? Just I told you a few minutes back, right? If I assume this is the structure of benzene, this structure of benzene is not going to explain all the properties of it, right? Because we know for the benzene, all the bond lengths must be equal, but as per this structure, all the bond lengths won't be equal. Yes. So this is the structure which is not explaining all the properties of benzene. So what I should get into my head, I should straight away get something into my head that benzene must be exhibiting resonance. That's why its single structure is not explaining all the properties of benzene right here. Yes. Correct? Yes. Now people, now before talking about what this resonance is all about, I told you why this concept was given. Why this concept was given? Because some structures couldn't explain all the properties of a molecule, right? That actually implied that the molecule exhibits resonance. Yes. Now what this resonance is all about? Before talking about that resonance, I need to give you some basic things right here which you must know before starting the resonance over here. Let's talk about those basic things right here first, okay? Right? Okay. The first thing which I'll be writing over here, see, that's something called as localized electron pair. Okay, I have used a term right here, localized electron pair. What is this localized electron pair all about? Remember, when an electron pair is shared only between two atoms, whenever the electron pair is shared only between two atoms, we call that electron pair as the localized electron pair. We call that electron pair as the localized electron pair. Yes. Okay. For example, like this. Let's say I've got A single bond B. Now this is one more electron pair between A and B. This electron pair is just between two atoms, right? It is just between two atoms. It is being shared by two atoms. Whenever electron pair like this is shared between two atoms, we call this electron pair as the localized electron pair. We call this electron pair as the localized electron pair, which is just shared between two atoms, right? Similarly, if I talk about this one, say on oxygen you have got a lone pair. This lone pair belongs to oxygen. This lone pair belongs to oxygen. I'll be calling this lone pair as the localized lone pair, right? This electron pair, it is shared between only two atoms. I'll be calling this electron pair as the localized electron pair. And this lone pair, which is of oxygen basically, okay, I'll be calling this as the localized lone pair of oxygen right here. Yes, I can say that. Okay. Now people, after this, there is something called as delocalized electron pair. What is delocalized electron pair all about? Okay. Remember, a pair of electron which is shared between more than two atoms. Whenever I'll be having such pair of electron which will be shared between more than two atoms, we call that electron pair as the delocalized electron pair right here. For example, have a look. See, let's say I've got something like this: A single bond B single bond C, right? For example, at one instant I could see the electron pair between A and B. At another instant, what I could see is, I saw the electron pair, I saw the same electron pair between B and C after some time. Yes, correct. See, at first instant, I saw the electron pair between A and B. After some time, I saw the same electron pair between B and C right here. So can I say the same electron pair is being shared by more than two atoms? We call this electron pair right here as the delocalized electron pair, which is shared between more than two atoms right here. Okay. So localized electron pair is the one which is shared by two atoms. Delocalized electron pair is the one which is shared between more than two atoms. Okay. Got it? Now guys, now the point is which electrons are delocalized, which electron pairs are delocalized. Okay. Remember, a high energy electron pair can be delocalized like your pi electrons. What does that mean? What does that mean? Understand that as well. What I said right here, first thing, a pair of electrons that is shared between more than two atoms, we call that pair of electron as the delocalized electron. Now, which electron pair will be delocalized? That electron pair which will be having high energy. A high energy electron pair can be delocalized, and the example of that delocalized electron pair is going to be the pi electron, right? Okay. Now the point is, how come pi electrons have got high energy? Why we call these pi electrons as high energy electrons? Why we call the pi electron pair? Why we call the pi electrons? Why we call the pi electron pair as the high energy electrons? High energy electron pairs, right? There's a point. There's a reason for that. Okay. See guys, I hope you would have studied chemical bonding. Yes, I hope you would have studied chemical bonding. In the chemical bonding, you would have discussed one topic called as VBT. Okay. And VBT explains the formation of sigma bond and the pi bond due to the head-on overlapping as well as parallel overlapping, right? Due to the head-on overlapping, due to the direct overlapping, which bond is formed? Sigma bond is formed, right? And due to the parallel overlapping, which bond is formed? Which bond is formed? Due to the parallel overlapping, I must say the pi bond is formed, if you remember, yeah? Correct? Now we will have a look. Let's say this is one atom which I have. Let's say this is the nucleus of one atom, correct? Let's say this is one orbital, okay? Let's say this one orbital of it. This is one more orbital of one more atom, okay? And this is the head-on overlap. So over here, which bond is formed? Sigma bond is formed, correct? Let's say this is one more orbital of this atom. Let's say this one more orbital of this atom. Can I say they are going to show the sideways overlap, parallel overlap, which leads to the formation of pi bond. So right here, which bond got formed? Pi bond got formed, okay? Right? Can I say this electron density right here, it is under the influence of, it is under the direct influence of these two nucleuses, right? Can I say this electron density right here, which led to the formation of sigma bond, it is under the influence of two nucleuses directly? Yes. But what about this electron density, guys? What about this electron density? Is this under the influence of two nucleuses directly? No way. No way. That electron density which experiences more force of attraction, that electron density, we say it has got less energy. Okay. And that electron density which experiences less force of attraction from the nucleus, we say that electron density have got higher energy, right? Higher energy means, that's what I told you, right? That's what I told you a few minutes back. A high energy electron pair can be delocalized like pi electrons. This is basically the pi electron density, and pi electron density is having high energy. And remember, only high energy electron pair can be delocalized like your pi electron, which will be less under the influence of the nucleus. Yes, exactly right. Right? Is it clear till here? Is it clear till here? Yeah. Let me know in the chat box fast. Yeah. Yes, Ashita, I'll be giving the examples also. Just wait for it. I'll be giving the examples. This is just starting. Wait. Okay. Right? Okay. Now, guys, we got to know high energy electron pair can be delocalized like your pi electrons, and the delocalization of these pi electrons is what we call as resonance, right? Delocalization of these pi electrons is what we call as resonance. Now the point is, what is this delocalization of pi electrons? Yeah, that's something which we should know first, right? What is this delocalization of pi electrons? First thing which I told you, a pair of electron which is shared between more than two atoms, that's what we call as delocalized electron pair. Right? Now, which electron pairs can be delocalized? Those electron pairs which will be having high energy, those are going to be delocalized like your pi electrons, right? And the delocalization of these high energy electrons, delocalization of these pi electrons, that's something which we call as resonance. Now the point is, what is this delocalization of pi electrons all about, right? What is this delocalization of pi electrons all about, right? Nitya, let me tell you, the sigma electrons are under the subjugation of more attraction between the nucleus, right? More attraction actually means it has got less potential energy, right? Something which we discuss in physics. Whenever there are attractions, energy is released, less energy is there with the system. Less energy means more stability, right? In case of pi electrons are under the less influence of the nucleus, right? So there'll be less attraction on that. If there is less attraction on the pi electrons, the pi electron energy will be definitely more. Yeah, I hope you got it. Yes? Okay, got it? Yes, Vulavu, I am taking class on the real Vedantu platform also. Yes, absolutely. All right, see guys, understand now. So I hope these 3 points are clear. Now the point is I told you delocalization of pi electrons is something called as resonance. Now what the point is? The point is, what is this delocalization all about? What is this delocalization all about? Let's understand the concept of delocalization right here, okay? In order to make you understand the concept of delocalization of pi electrons, I'm going to take the orbital approach of resonance, by means of which you'll get the idea of what is this delocalization of pi electrons all about, yeah? See, I hope you remember the structure of benzene. Yes. What is benzene? It is a 6-membered ring. Yeah. See, if I'm making a structure of benzene like this, isn't it a 6-membered ring like this? Correct? In case of benzene, do you remember in case of benzene, every carbon is sp2 hybridized? Yes, every carbon is sp2 hybridized, right? Right? These are the sigma bonds between carbon, carbon, carbon. These are all the sigma bonds. Yes. Okay. And which hybridization this carbon undergoes right here? sp2 hybridization. Can I say there'll be one empty p orbital on this carbon right here? Yes. Which will be perpendicular to the plane containing these bonds, containing these sigma bonds. Absolutely. There will be one more empty orbital like this. There'll be one more empty orbital like this with this one. There'll be one more like this, one more like this, one more like this. On every carbon atom, you'll see one unhybridized p orbital on every carbon right here. Yes. Now people, sigma bond has already got formed between the carbon atoms, right? Now it is the turn for what? Now is the turn for pi bonds, right? See, this sigma bond, as I told you earlier, it's formed by the direct overlap, okay, direct overlap of the orbitals, of the hybrid orbitals, direct overlap of the hybrid orbitals, direct overlap, direct overlap, direct overlap. Now what is going to happen? Now there will be parallel overlapping. Now there will be parallel overlapping. All these empty p orbitals, they are parallel to each other. They are parallel to each other. Now the cases arise right here. There can be parallel overlapping, and that parallel overlapping can be done many ways. How? Have a look. See guys, the first possibility which I'm writing over here, first of all, let me make the 6-membered ring right here again. The first possibility which I'm showing you right here, the first possibility which can happen, this one and this one will show overlap, okay? At the same time, this one and this one will show overlap. At the same time, this one and this one will show overlap, right? And this is, first of all, the parallel overlapping, and parallel overlapping leads to the formation of what? It leads to the formation of pi bond, right? So due to this overlap, can I say one pi bond would have got formed right here? Similarly, due to this partial overlap, due to this parallel overlap, one more pi bond would have got formed right here. Due to this, one more pi bond would have got formed right here. So this is one probability. This is one probability that these two orbitals would have overlapped, these two orbitals would have overlapped, and these two orbitals would have overlapped parallelly, which would have resulted into this structure. This is one probable structure, I will say, which I'm assuming something like this would have happened, right? At the same time, there is one more possibility at the same time. Let's assume these orbitals have not overlapped. Let's assume this orbital, I'm changing the color. Let's say this orbital and this orbital has overlapped, okay? Let's assume this orbital and this orbital has overlapped. Let's assume this orbital and this orbital has overlapped, okay? Which would be giving me one more structure like this, which is going to be one more probable structure of benzene. This is going to be one more probable structure of benzene, okay? And due to this overlapping, a pi bond would have got formed right here, a pi bond would have got formed right here, a pi bond would have got formed right here. So I got two probable structures of benzene right here. But people, if I consider any one of the probable structures among these two, this is one probable structure, this is one more probable structure, which would have happened, right? Is this structure explaining all the properties of benzene? No way. Why is that? Because we know, as per your benzene is concerned, it has got identical bond lengths. But as per this structure, right here, double bond, okay, right here, single bond, right here, double bond, right here, single bond. So all the bond lengths are not going to be identical. Yes, right? All the bond lengths are not going to be identical. Yes, correct. So this structure is not explaining all the properties of benzene. Similarly, this structure is not explaining all the properties of benzene, right? This structure is not explaining all the properties of benzene, correct? But people, at the same time, I can say something. This structure is giving me some information about benzene. This structure is also giving me some information about the benzene, right? This is giving me some information about the benzene. This structure is also giving me some information about the benzene, right? Correct? Now what I'll be doing right here, what is going to be the actual structure of benzene? Correct? If this is not the actual one, this is not the actual, what is going to be the correct one? In case of benzene, what happens? All these p orbitals, they are going to overlap parallelly, simultaneously, right? They are going to simultaneously overlap parallelly right here, which leads to the formation of one angular electron density on the top of the plane, which consists of the sigma bonds. Yeah. Yes, let me show it like this. Let me show it to you like this. See, the actual structure of benzene is going to be like this. This is going to be the 6-membered ring in which you have got the sigma bonds, 6 sigma bonds, right? Okay, right here in this one. Okay. Now people, on the top of it, there is going to be electron density, one angular electron density. I'll call this as pi electron density, okay, on the top of it. correct? This is your pi electron density. This is your pi electron density. So actually in case of benzene, all these pi orbitals, they overlap partially but simultaneously, which leads to the formation of one angular electron cloud right here. Okay, I can see that, yes. Now people, if I ask you, in this structure which I got, this is the actual structure of benzene now. This is the actual structure of benzene in which these p orbitals, would have partially overlapped simultaneously, okay? If I ask you, can I localize the pi electrons between the two carbon atoms right here? I cannot say whether the pi electrons are between these two carbon atoms. I cannot say whether the pi electrons are between two carbon atoms. I cannot say whether the pi electrons are between these two. No, I cannot check that, right? So I can say pi electrons right here in this structure are delocalized. Yes. Right? Right? I cannot say. I can say pi electrons right here are delocalized. I'm unable to locate them between two carbon atoms, right? I have no idea whether the pi electrons are between these two. No way. So I'll say this is the delocalization. This is something called as delocalization of pi electrons, right? And this delocalization of pi electrons is what we call as resonance. Got it? Got it? Let me know in the chat box. Yes. Let me know in the chat box if it's clear. Dusted? Yes, got it? यार अभी मेरे को जैकेट मिला ही नहीं वेदांतु वाला इसलिए स्वेटर पहनी हुई है. Okay, I hope this clear. I hope this delocalization of pi electrons is clear, right? Now people, if I ask you one thing, is this structure giving me the complete information about the benzene? No way. Is this structure giving? No. Right? That structure, that proposed structure, that probable structure which does not give me the complete information about the actual molecule, that probable structure is something called as canonical structure or resonating structure. I'll be calling this structure and this structure, I'll be calling these two structures as the canonical structures, canonical forms, or the resonating structures of the benzene, right? And how do I represent benzene actually now? How do I represent the true structure of benzene? True structure of benzene I'll be representing like this, right? This is the angular electron density which is on the top of the plane which contains these sigma bonds right here. Yes. This is something which I called as the true structure, or this is something which I call as the resonance hybrid. This is something which I call as the resonance hybrid right here. Yes, is that clear? Got it? Got it? Very, very simple. Can I say this resonance hybrid, it is basically the combination of these two? How come this resonance hybrid is combination of these two canonical structures, these two resonating structures? How come? Have a look. As per the first one, as per this structure is concerned, between these two carbon atoms, there is a single bond. But as per this structure, just a second guys, wait, where is that bond? Just a second. See, as per this structure is concerned, between these two carbon atoms, there should be double bond. But as per this structure is concerned, between these two carbon atoms, there should be single bond, right? Right? So what is going to happen? As per this structure, there should be a single bond. As per this structure, there should be a double bond between these two, right? Can I say this bond actually, in case of resonance hybrid, it's not going to be a double bond exactly. It's not going to be a single bond exactly. It's going to lie between single and double bond, right? That's why I've shown it like this over here. Yes, correct. Can I say it's basically a partial double bond right here? It's not exactly the double bond. It's not exactly the single bond. It lies between single and double right here. So I'll be calling this as the partial double bond right here. Yes, correct. Right? Priya, you can show that as well. Yeah. This is going to be what? It's going to lead to the formation of partial double bonds right here. And people, as you all must be knowing, if I talk about single bond, if I talk about double bond, and if I talk about partial double bond, can you let me know the strengths of these pure single bond, partial double bond, and the actual double bond? Can you let me know about the strengths of these? Can I say bond strength of the actual double bond is maximum, followed by the partial double bond, followed by the actual single bond, right? Wherever bond strength will be more, can I say bond length is going to be less there, right? Right? Can I say bond length is going to be Can I say bond length is just going to follow the opposite order? This is the order of bond length. This is the order of what? Bond strength right here. Yes? Exactly. Exactly. Yeah? Right? Well, people, I've summarized all this. I've summarized all this beautifully in one slide where all these points are written. First thing, this is the actual structure. This is the true structure which explains all the properties of benzene, right? So I'll be calling this as either as the true structure or I'll be calling this as the resonance hybrid. Okay. Now, people, this is one of the probable structure of benzene. Okay, there is probability that benzene sometimes could have formed this structure. There is probability that benzene could have sometimes formed this structure. So this benzene, it's clearly not giving me the 100% information. I mean, this structure is not giving me clear information, 100% information about benzene. This is not giving me 100% information about benzene. So I can say this is something, this is the structure, the hybrid which I'm saying. This is the structure which I got by combining these two. I'll assume something like this. I'll assume this structure is giving me 50% information about benzene. This structure is giving me 50% information about benzene. If I'll combine the two informations, I'll be getting something like this, which is what we call as a resonance hybrid. Yes? Right? Exactly. Exactly, guys. Exactly. Yeah? Okay. 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 Wonderful. All right. Let's move on. Let's move on. See. Few minutes back, whatever I told you till now, I've summarized it, everything beautifully right here. See, that structure which contains the localized bonding but cannot explain all the properties of molecules are called as theoretical structures, resonant structures, or canonical structures. Yes? Yes? Right? See guys, I'm going to make it again. See, if you remember, this is something which I call as resonance hybrid right here. Yes, this is something which I call a resonance hybrid right here. Correct? Well, guys, it's one of the probable structure of the benzene. This is one of the probable structure of benzene, right? And at the same time, we have got one more probable structure of benzene, right? Just a second. This is one more probable structure of benzene. This is what we call as hybrid, right? Resonance hybrid. Correct? People, can I say in this structure, I can easily locate where the pi electrons are? Yes, I can clearly say in this structure, pi electrons are between these two. Pi electrons are between these two carbon atoms. Pi electrons are here. Similarly, in this structure, I can easily locate the pi electrons. Can I say over here, this structure contains localized pi electrons. This structure contains localized pi electrons. So these localized structures, these structures which contains the localized bonding but cannot explain all the properties of molecules, these are what we call as theoretical structures, resonating or canonical structures, right? Right? But this one, it contains delocalized pi electrons right here. Okay? You cannot exactly locate where the pi electrons are. No way. You are not going to locate that. Yeah? You cannot do that. Correct? You cannot do that. So I'll be calling this as hybrid. And this will clearly give me the idea about, this is going to give me all the information about benzene, this hybrid, right? Yes. Yes. Correct. Remember, guys, the stability of hybrid, the stability of resonance hybrid, okay, the stability of this hybrid is always going to be greater than the stability of its canonical structures. Remember that at the same time, okay? Why is that? Why is that? Because over here, the pi electrons are delocalized. They are under the influence of more than two nucleuses, right? Right here, I can say pi electrons are delocalized. They are under the influence of more than two nucleuses, right? So there will be more force of attraction between them. There will be more force of attraction on those pi electrons, right? Correct? More the attraction, less the energy, more the stability. Can I say this hybrid is definitely going to have less energy than the rest of its canonical structures? Yes. Can I say that? Yeah. So less energy means more stability. Definitely the hybrid is going to be the maximum stable among the rest of the canonical structures of it. Yeah. Let's move on. This is something which I told you. None of the canonical structure is the true structure of benzene, right? Because none of the canonical structure gives you the exact 100% data about the actual benzene, right? Yes? Okay. And people, one more thing. That structure which contains the delocalized bonding, but can explain all the properties of the molecule is something called as a resonance hybrid, right? The example is this one. This is the resonance hybrid of benzene. Correct? Yes? Absolutely. I hope this is clear. right? Okay, let's move on. See guys, as I told you, due to the delocalization of pi electrons, what happens? Partial pi bonds are formed, partial double bonds are formed. Yes. And what about the bond length of the single bond, partial double bond, and exact double bond? This is something which I told you a few minutes back. This is the order of the bond length, and this is the order of the bond strength. Yes, just opposite of the bond length. This is something which I told you a few minutes back, right? I've summarized it, everything right here. You can take the screenshot of it if you want, or you'll be getting the PDF of it after once the session ends in the Telegram. Yeah. Okay, let's move on to something called as pi electrons. Well, people, pi electrons, talking about pi electrons. Pi electrons are actually of two types. One is called as the real pi electrons, another one is called as differential pi electrons. What are real pi electrons? Real pi electrons are there in your double bond as well as in triple bond. Those electron pairs which are there in double bond or triple bond, those pi electron pairs which are there in double bond or triple bond, those are what we call as real pi electrons. Okay, and those electrons, like your lone pair, or the negative charge with the lone pair, this is what we call as differential pi electron. Okay, so I classify pi electrons into two types. One is called as real pi electrons. Real pi electrons are the ones which are there in the double bond, those pi electrons which are there in the double bond, and those pi electrons which are there in the triple bond. I call these electrons as the real pi electrons, and the lone pair is called as differential pi, and the negative charge with a lone pair is also called as what? It's also called as differential pi electron. Remember this right now. Okay. What about the energy order of these real pi electrons and differential pi electrons? What about their energy order? Remember the negative charge with a lone pair. The negative charge with a lone pair, it's going to have maximum energy, followed by lone pair, followed by the real pi electrons. Okay. This is the energy order of these pi electrons right here. Remember this. Correct? That's great, Yashwant, that's great. Okay, this is the actual energy order of these pi electrons. First, negative charge with a lone pair with maximum energy, followed by a lone pair, followed by the normal pi electrons, real pi electrons. Yes? Okay? Exactly. This differential pi, it looks like an emoji, yeah? Okay, let's move on, guys. Let's move on. Now the point is, what are the conditions for the resonance? Okay, what all conditions must be satisfied so that we can explain the resonance? Yeah. Okay. First condition, and the very important condition: presence of parallel p orbitals with high energy electrons coplanar to each other. Right. This is the first condition. This is the first condition for the resonance. There should be parallel p orbitals between two adjacent carbon atoms. There should be parallel, if I'm talking about carbon, right? If I'm talking about benzene, for example, okay? There should be what? Parallel p orbitals with high energy electrons, which must be coplanar to each other. What does that mean? Let's say this is your p orbital. Let's say this one more p orbital, one more p orbital, one more p orbital, one more p orbital, right? One more right here. Okay, all these p orbitals first of all must be parallel to each other, right? They should contain what? High energy electrons. They should contain high energy electrons. They should contain high energy electrons, right? And they should be coplanar to each other. This is the nucleus of one, this is the nucleus, this is the nucleus. All these nucleus, they should lie in the same plane like this. Yeah, they should lie in the same plane like this, correct? Now people, how many possibilities of parallel overlapping are here? How many possibilities of parallel overlapping are here? One possibility is this can be the parallel overlapping this, right? This one, correct? This one I'll show right here, this one I'll show right here, this one I'll show right here. This is first probability of parallel overlapping, right? This is first probability. Second probability would have been like this. Second probability would have been like this. This should have been the overlap. This should have been the overlap, right? Similarly, this should have been the parallel overlap. This should have been the parallel overlap. Similarly, this should have been the parallel overlap. This should have been the parallel overlap, right? Can I say due to the delocalization of these high energy electrons, every bond got the partial double bond? Yes, it got the partial double bond character. Every bond got the partial double bond character right here due to the delocalization of these high energy electrons. Yes, I can say that. Yes. So remember guys, the first condition for resonance is there should be the presence of the parallel p orbitals with high energy electrons, and they must be coplanar to each other. Point number one, right? Now point number two, what is that going to be? See, this is something which I told you a few minutes back, right? Due to the delocalization of pi electrons, the pair of electrons is subjected to more force of attraction? See, a localized electron pair lies between two nucleus. A delocalized electron will be shared by more than two atoms, right? More than two atoms. That means that is subjugated to the attraction by more than two nucleuses, right? I can say that. Due to the attraction, energy of the system decreases. If the energy of the system decreases, stability increases. So can I say due to resonance, due to the delocalization of pi electrons, the pi electron pair is subjected to more force of attraction, okay, due to which potential energy decreases, stability increases. That's why we say resonance increases the stability of the molecule. Yes. Let me know in the chat box if it's clear. Yes. Right? Exactly. Let's move on to one more point. See guys, resonance hybrid is always more stable because resonance is present in the hybrid, not in the canonical structure. Yes, delocalization is present actually in the hybrid. It's not present in the canonical form. It's not. See, canonical form, it cannot explain all the properties of the molecule, right? It cannot explain all the properties of the molecule. Resonance, delocalization is present in the hybrid. It's not present in the canonical form. In the canonical form, the pi electron pairs are localized. Yes, those are localized. I hope this point is also clear to you, right? Resonance hybrid is always more stable because resonance is present in the hybrid, not in the canonical form, right? Point number next. All the canonical forms should have almost same energy. All the canonical forms should have, this is one more condition for the resonance, okay? Whatever canonical forms will be having, they must have almost similar energy. For example, let me make you understand like this. Let's say I have got a hybrid, or I'll call that as the true structure, which I'm representing by T. Let's say this T is the true structure of the molecule, right? Let's say it has got few canonical forms. I'm proposing one of its structure is, for example, C1. I'm proposing one of its structure is C2. I'm proposing one of its structure is C3. I can call these only the canonical forms if they'll be having similar energies, if they'll be having almost same energy, right? If some other guy comes, he gives one more probable structure of this T right here, which is C4. But let's assume the energy of C4 is far greater than the rest of these forms. I won't be considering this as the canonical form. I won't be considering this as the canonical form. Yes, I won't be considering this as the canonical form right here. Okay, remember this. Okay, now out of all the canonical forms, that structure which is more stable, that gives the better representation of the true molecule. Yes, okay. So what this statement is all about, see, we know out of all the resonating structures, out of all the canonical forms, there will be one of the canonical form that is going to be highest stable among all the canonical forms. Yes, absolutely right. Can I say that canonical form which is going to be maximum stable among all the canonical forms, can I say that will be more like your resonance hybrid? Can I say that will be more like your true molecule? Right? Right? Yes, I can say that. I can say that. Yes. So this is something like that which is written over here. Out of all the canonical forms, that structure which is more stable gives the better representation of the true molecule, right? That canonical form which is the most stable among all the canonical forms, I will say that will be more like your true molecule, right? That will be more like your true molecule. Okay, remember this point as well. Now, all the canonical forms should have same total sum of shared and unshared electron pairs. What does that mean? Let's say I'm giving you two canonical forms right here. These are the two canonical forms of some molecule over here, of some molecule, okay? These are the two canonical forms of some molecule right here, okay? I will be only calling them as the canonical forms if they have got equal number of electron pairs. If both the canonical forms will, if both the forms will have the equal electron pairs, then only I will be calling them as the canonical forms, okay? How come I'll be checking that? How come I'll be checking that? Have a look. Have a look, guys. Have a look, guys. Understand. See, this is first of all one bond. That means one electron pair. These are three bonds. That means three electron pairs. So 1 plus 3. This is one more electron pair right here. So 1 plus 3 plus 1. That means over here in this form, we have got total 5 electron pairs. So here also should be 5 electron pairs, then only I can call them as the canonical forms, right? Yes, have a look, have a look. This is a single bond, that means 1 electron pair, right? Double bond, 2 electron pairs. lone pair, that means 2 electron pairs, 2 to 4, 1, 5. So both the ones have got equal number of total electron pairs right here, okay? Both the ones have got equal electron pairs right here, okay? So this is one most important condition, guys, here, okay? What is that? All the canonical forms, they must have same number of total electron pairs, okay? If the total electron pairs are not same in the two forms, I won't be calling them as the canonical forms. Remember this as well, right? Okay, now let's move on. Let's move on and let's talk about the types of conjugation. Let's see wherein we can use the concept of resonance. How the delocalization of pi electrons actually takes place. Let's get to know that. Okay, the first form by means of which I'll show you how the delocalization of pi electrons is taking place. For that, in order to make you understand that, I need to show you the pi sigma vacant orbital conjugation. Okay, whenever you see pi sigma and vacant orbital, whenever you see pi sigma and vacant orbital like this, okay, remember at that time there will be resonance, there will be the delocalization of pi electron, right? And this delocalization of pi electron, how come it takes place? See guys, let's say this atom A between, let's say this is atom B right here, and this is the empty orbital of that. This is the empty orbital of atom B. I'm just making you understand. After this, I'll be giving you the actual examples. So right here, can I say, let's say this atom C over here, okay? Can I say this is pi, this is sigma, and this empty orbital, okay? So what is going to happen? Conjugation, which conjugation? Pi sigma empty orbital conjugation. Whenever you see pi sigma empty orbital conjugation, remember there will be the delocalization of pi electron, and that delocalization of pi electron is something called as resonance. Yes. So what you'll be doing right here, just in order to make its other canonical forms, canonical forms, what you'll be doing, you'll be just, let's say you have got something like this. Just a second. Let's say there's a positive charge over here. Okay. Let's say there's a positive charge over here. Okay. Now guys, in order to make one more canonical form, just remove one of the pi bond and keep this pi bond over here instead of this one. Okay, wait, let me make it separately so that there won't be any sort of doubt to you. Okay, what I'll be doing, first of all, I'll be removing one pi bond, and this pi bond I'm going to take over here directly without doing any sort of disturbance. It's going to be C. Now it's going to be single bond A, it's going to be double bond B right here. Okay, right? Now guys, see, over here there was a double bond, okay, right here we had the pi bond, but now there is no pi bond, so I'll be representing it by the positive charge. I'll be showing the positive charge over here. Now guys, this pi bond is right here in between. Over here there was positive charge. Now due to the formation of pi bond, there'll be no positive charge right here. This is one more hybrid, this is one more canonical form of this structure. This one, yes. These are the two canonical forms. This was one canonical form, this is one more canonical form, right? If I need to make the resonance hybrid, how will I be making that? I'll be just combining these two, right? I'll be combining all the resonating structures. As per this resonating structure, A and C should have double bond. As per this one, they should have what? They should have single bond. So if I'll combine them, that means A and C will be having partial double bond. Yes, it'll be like this. I'll be writing A, over here I'll be writing C, so it's going to be like this, yeah? Correct. As per this one, A and B should have single bond. As per this one, A and B should have double bond. So it should have partial double bond like this, right? It should have partial double bond like this, correct? Let me write this B over here, correct? Now, as per this structure, C should have positive charge. As per this structure, C should not have positive charge. So I'm going to represent it as delta positive, slight positive, yes? Similarly, as per this structure, B should have positive. As per this, B should not have. So I'll be showing it plus delta over here. This is going to be the resonance hybrid right here. Yes. Akshita, just take the video a little back. It will be automatically a replay, okay? Right? Now, people, let me give you the exact examples of how to understand this type of conjugation, which is pi sigma vacant orbital conjugation, yeah? Right? Yes, Subhash, I teach in V Enthuse also. Okay, yes, I teach in V Enthuse also. Okay. The first example which I'm giving here right now, okay? This is something which I'm giving to you, okay? This is one canonical structure of one molecule. Some molecule is there, this is one of the canonical structure of it, okay? I need to make few more canonical structures of this one. Let me see how many canonical structures can get formed. See, first thing, do I have a pi bond? Yes. Do I have a sigma bond? Yes, right? Is there any vacant orbital with this carbon? Let's check that. People, I hope you remember what is the outermost configuration of carbon. It is 2s2, 2p2. Yes, it is 2s2, 2p2. It's going to be like this. It's going to be like this, the outermost configuration of carbon. Yes, correct. Now, due to excitation, can I say one electron will be removed from here? So that electron will be going right here. Yes, that electron will be going right here. It is arrow like this. Yeah, that electron will be going right here. Right? This is the excited state of the carbon. This is the excited state of the carbon. Correct? Now, right here, carbon has got the positive charge. That means one of the electron is removed from here. Okay, so I'll say one p orbital is empty right here. Okay, now people, can I say the carbon can undergo sp2 hybridization? This carbon right here is undergoing sp2 hybridization. So how many atomic orbitals are intermixing right here? 3 atomic orbitals are intermixing, which leads to the formation of 3 hybrid orbitals, 3 sp2 hybrid orbitals, right? Now people, I'm going to arrange, as per your bonding is concerned, I'm going to arrange these 3 sp2 hybrid orbitals in such a way that there should be minimum repulsions among them. Yes, let me make the structure like this. Let me make the structure again like this so that you get it properly, okay? Let me make a structure like this. This is CH. Okay, this was C, which I'm talking about right here. This is C, whose configuration I'm talking about right here. It underwent sp2 hybridization, right? It underwent sp2 hybridization, which led to the formation of 3 sp2 hybrid orbitals. This is one. This is one more, and this is one more. Yes, right? This hybrid orbital will show direct overlap. It will show direct overlap, head-on overlap with this carbon, right? But people, every hybrid orbital has got one electron right here. Every hybrid orbital has got one electron right here. One hydrogen would have come from this side, done the overlap. One hydrogen would have come from this side, done the overlap. But people, this carbon, it has got one empty p orbital, one pure p orbital right here, correct? Which is empty. Can I say I got pi sigma empty orbital, right? Can I say it is the conjugation which I'm talking about right here? This is the conjugation which I'm talking about right here. This is pi, sigma, and empty. Will it show resonance right here? Yes. Definitely, guys, it will show resonance because it is the same conjugation which I'm talking about right here, pi sigma vacant. Whenever you see pi sigma vacant orbital, there will be the delocalization of pi electrons. Yes. Now, how this delocalization of pi electrons will take place right here? Understand what I'll say. See, guys. See, first of all, I got to know that conjugation is there. That means what will happen? Delocalization of pi electrons is going to take place. Okay. Now, the first thing which is going to happen right here, just remove this double bond. Take this double bond right here. So the structure which you will be getting, see, if you are removing double bond from here, there'll be the positive charge on this carbon right here. There'll be a positive charge on this carbon right here. Yes, single bond. Now CH, right? I'm putting, instead of this double bond, I'm putting the double bond right here. It's going to be double bond like this. So it's going to be CH2. Now it had the positive charge. Now due to the formation of double bond, that positive charge would have gone. Yes, this is the one more canonical structure of this. Okay, so how many canonical structures right here? 2 canonical structures right here. If I need to make the resonance hybrid, will I be making that? Yes, I'll be combining the 2. Right here double bond, right here single bond. Yes, so it should be like this. H2C, it should be like this. This should be CH. Yes, single bond, over here double bond. So there'll be the partial double bond like this. So it is CH2. Correct. Now, positive charge is on which atom? So, as per this structure, positive charge should be on this atom. As per this structure, positive charge should be on this atom. So, I'm making it by delta. This is the resonance hybrid, which is definitely going to be stable than this as well as this. Yeah. This is going to be more stable than its canonical forms. I hope you know that. Yeah. I hope you know that. Correct. Yes. Awesome. Bro, ye English channel. I'm not supposed to talk in Hindi. People, let me know in the chat box if it's clear till here. Let me know in the chat box if it's clear to everyone, so that I can move on and give you a few more things. Yeah. Yeah. Okay. Wonderful. So this is one more canonical form, and this is the true molecule hybrid, which I'm calling. Yes. This is the hybrid. Okay, people, there are a lot of exceptions in this as well. Okay, you need to know those exceptions. But before talking about the exceptions, I'll show you how to draw the resonating structures now. Now we will see. First thing, right here I've got a pi bond. This is pi, this is sigma, and this carbon is sp2 hybridized. It will be having a p orbital, empty p orbital, right? Which will be parallel to this one, right? This will be parallel to this one. So can I say this is pi, sigma, empty p orbital, right? So this is the conjugation. It's going to show conjugation. So first kind of canonical structure which I have right here. The second which I'm going to make, just remove this double bond, keep it right here. So the structure is going to be like this. Just put the double bond it's going to be like this. Just a second. It's going to be like this. See, I'll remove this double bond. There'll be the positive charge on this carbon, right? So right here, it's going to be CH2. This positive charge would have got compensated by the presence of this double bond and have got nothing would do with these double bonds right here. Can I say in this structure, again, I got pi sigma positive charge, pi sigma p orbital, empty p orbital, right? Can I say it's going to show conjugation? This, keep this double bond right here, correct? Can I say one more structure is going to be like this? It's going to be like this. Just have a look, guys. Just have a look. It's first of all double bonded CH2. I didn't do anything with this. Yes, correct. Now, since I'm removing double from this carbon, so this carbon is going to get positive charge, right? And just put a double bond right here. By putting the double bond, this positive charge would have got nullified right here, and one more double bond similarly like this. Yes. Can I say again in this there is pi sigma and positive charge conjugation? Yes. So can I say one more resonating structure will be like this? One more resonating structure will be like this. Let me make the resonating structure like this. Yeah. See, guys, I'll remove the pi bond from this carbon, so get the positive charge, right? I've kept the pi bond right here. Yes. Due to the formation of this pi bond, can I say this positive charge got nullified? Yes. There is one more pi bond like this, and this is as it is, right? Right? I can say that. Now, people, can I say I got one more conjugation? Pi sigma positive. Pi sigma positive means pi sigma MTP orbital, right? Can I say it's again going to show conjugation? Absolutely. So one more canonical form of this is going to be like this. One more canonical form of this is going to be like this. It's going to be, have a look. It's going to be like this, yeah? Correct. Now there'll be a double bond right here. On this CH2, there'll be a positive charge, right? Double bond, double bond, double bond right here. Okay. So how many canonical structures do we have? People, this was not the actual molecule. This was the canonical. This was one of the canonical structure. And I made rest of 4 canonical structures, right? Yes. So there are total 5 canonical structures right here. Can I say first one and last one? Are these same or different? Is the same or different? First one and last one. First one. This is what I was expecting answer from someone. See, first one and last one, these are not same, these are different, but they have same energy, same stability. Okay, first one and last one, it has got first and last, they have got same energy, same stability, but they are different, right here. This is the localized electron pair between these 2 carbons, but right here there's a single bond, right? So this structure and this structure, both the ones are different, right? Yes. So remember, first one and last one, these are different structures, but having same stabilities. Yes. I hope this is clear. Right? Exactly. Wonderful. Let me move on to a few more. See, this is something which I told you, this is something which I told you, this is something which you'll be getting in the form of PDF, right? Okay, if I need to make the resonating, if I need to make this, what do we call this as resonance hybrid? How the resonance hybrid will look like? What do you think? How the resonance hybrid will look like? Yes, aim the aims. There is exception. You'll be getting that in some time. Let me finish it off first. See, if I need to make the resonance hybrid, in the resonance hybrid, so right here single bond, double bond. So right here you'll be getting the partial double bond character. Okay. Everywhere in the ring also over here partial double bond character. Right. There'll be the positive charge over here. There'll be the delta positive on this side. Right. There'll be delta positive on this side, there'll be delta positive on this side. So my resonance hybrid right here is going to be like this. My resonance hybrid is going to be like this. I'll make the circle right here, okay? And this is your CH2, correct? This is a dotted circle, guys. It's not a complete, it's a dotted circle, right? And delta positive right here, okay? Similarly, delta positive right here, correct? Similarly, delta positive right here, right? Similarly, delta positive right here. Can I say this is going to be the resonating hybrid right here, right? Clear to everyone? Yes. Let's move on. Let's move on to a few more examples. See, guys, this is the resonance hybrid which is formed right here. Yes, like this. Okay. Well, people, let's talk about the third example right here. Will there be resonance in this one? Will there be resonance in this one? Yashwant, I'm not talking about the stability of anyone. Stability, I'll be talking differently. Wait for that. I'm just showing you how to draw the structures first, okay? After that, I'll let you know how to compare the stability of these, okay? So no need to hurry at all. We have got time. Chill. Chill. Okay. See, guys, right here, can I say this is first of all carbon, which is sp2 hybridized. sp2 hybridized means there will be one empty orbital, which I've shown you a few minutes back. How come there will be the empty orbital right here, empty p orbital right here? Yes, which is going to be the perpendicular to the plane which contains these bonds. Yes, perpendicular to, like this. This is going to be, this pen is going to be one lobe of that empty orbital, right? Empty p orbital. Yes, correct. Now people, can I say right here I got pi, sigma and empty p orbital, right? Pi, sigma, empty p orbital. Is it the conjugation which we are talking about right here? Yes. Can I say right here what is going to happen? Can I say right here resonance will happen, delocalization of pi electrons will take place. So my first resonating structure which is going to be like this. Just remove this pi bond, keep it here, correct? So the structure is going to be like this. Structure is going to be like this. First of all, I'm removing this pi bond from this carbon. So this carbon gets a positive charge, and since due to the formation of double bond, this positive charge is nullified. Yes, correct. This is one of the resonating structures, correct? Okay, now people, one more chance is there. Again, I got pi, sigma, positive. Pi, sigma, positive means pi, sigma, empty p orbital. Can I say now one more structure is going to be like this? I'm removing double bond from here. It's going to be positive. Yes, put the double bond right here, right? This positive charge would have got nullified. Yes, this is one more structure. This is one more resonating structure, correct? Now people, do you think this is pi, sigma and positive again? Will it show conjugation? If it shows conjugation, the pi bond will come here and positive charge will become here. Then these two structures are going to be same then. The structures are going to be same then, right? If I do one more transfer of these pi electrons right here, if I do one more this delocalization of pi electrons right here, it's going to be same as that of first one. Yes, it will form same as that of first one, correct? So how many resonating structures do we have right here? How many resonating structures do we have right here? We have got 3 resonating structures. Yes, 3 resonating structures, 3 canonical forms. What is going to be the resonating hybrid all about? Can I say your resonating hybrid will be like this? See, every bond is getting partial double bond character. Yes, every bond is getting partial double bond character. There will be positive charge over here. So this delta positive charge over here. So this is again delta positive charge over here. Again delta positive right here. This is the resonance hybrid whose stability will be more than that of these 3. Whose energy will be less than that of these 3. Right? And that one which is going to be the more stable, among all these canonical forms, that one, it will truly represent the true molecule. Yes, we can say that, correct? Oh, it's Priya's birthday. Happy birthday, Priya. Happy birthday. God bless you. Happy birthday. Harish, just do one thing. Take the video back. It'll be replay, bro. Take the video a little back. It'll be automatically a replay. Okay. Harish, what I'm saying, just drag the video a little back. It'll be automatically a replay, bro. Okay, let's move on to a few more. So this is something which I've shown you right here, this something, and this is, okay, people, one more important thing. Due to resonance, due to the delocalization, what is happening to the charge? Can I say charge is getting distributed due to this resonance? Can I say charge is getting distributed, right? Charge is getting distributed due to this delocalization of pi electrons, right? Due to the distribution of charge, what is going to happen to volume charge density? Can I say volume charge density will decrease? And if you remember in the first session, I've told you, volume charge density is inversely proportional to stability. If volume charge density of the molecule decreases, its stability eventually increases. Yes? Right? I can say that. Correct? Very simple this is. Yeah? Okay, so I can say simply, due to the distribution of charge, volume charge density what? Volume charge density decreases. Due to the distribution of charge, volume charge density decreases. And if the volume charge density decreases, I must say stability increases. Yes. Right? Exactly. Okay, let me know guys, will this molecule show resonance? Let me know in the chat box. Let me see how much concepts you got till now. From this question, I'll get to know, did you get the actual concepts or not? Let me know fast. Will this molecule show resonance? I'm waiting for your answers, guys. What do you think? Will it show resonance? So normally till now, what I told you, see, this is pi, yes, this is sigma, and this is sp2 hybridized carbon, so it will have empty p orbital. So this is pi sigma empty orbital, yes. So it should show resonance. So what do you think should be its structure? Its hybrid, sorry, its canonical form. It should be like this. Put the double bond right here. This should be CH2. This should be O, and right here this should be positive charge. So as per you, this should be this. This should be something. This should be its one more canonical form. But people, do you remember? Do you remember positive charge on an electron negative element makes it highly unstable? So this will be highly unstable. Its energy will be very, very high. Correct? So this is not going to be the resonating structure of this. Yeah? Yes? See, first of all, this is not some true structure. This is the canonical form. This is one of the canonical form, right? Its another canonical form was supposed to be this one. But as I told you, canonical forms should have almost same energies, right? But if this canonical form exists, its energy will be very, very high. But we know canonical forms, that canonical form whose energy will be very, very high or very, very less as compared to the rest of its canonical forms, that does not exist. So it does not exist, right? Right? And for the molecule to show resonance, there should be two canonical forms, but right here only one. So this molecule is not going to show any sort of resonance. Yes, I can say that. Correct? I can say that. Exactly. Exactly. हाँ यार हिंदी में क्या बोलो, इंग्लिश चैनल है. Sakleen, happy birthday bro, if it's your birthday. Happy birthday bro, happy birthday, God bless you. Okay, few more guys. See, this is one more interesting thing right here. This one more interesting thing right here, which I want you guys to take a note of carefully. See, the atom having positive charge, the atom having positive charge should have vacant orbitals. Then only it shows the sigma pi vacant orbital conjugation, which leads to the happening of resonance. Yes, right? Now guys, understand what is going to happen over here. Normally, if a normal person will think, he'll think like this. This is pi, this is sigma, and over here positive. So pi sigma positive charge, it will definitely show resonance, right? He'll make the structure and so on. But people, right here understand. Is the octet of nitrogen complete? It is making 3 bonds with 3 hydrogens, right? Like this. And 1 bond right here. Is the octet of nitrogen complete? Absolutely, octet of nitrogen is complete. Yes. If the octet of nitrogen is complete, can I say it's in its outermost shell there will be 8 electrons, right? Its outermost shell will be like this: 2s2, 2p6, right? Because its octet is complete now. 2s2, 2p6, right? Is there any vacant p orbital? Is there any vacant orbital in nitrogen? There is no vacant orbital, right? And for the resonance to happen, it should be pi sigma, and it should have vacant orbital right here. If it is not having any vacant orbital, can I say this one is not going to show any sort of resonance right here? Yes? Yes? Absolutely, guys. Absolutely. Now let me know in the second one. See, this is absolutely pi, this is sigma, and this is positive. Normally I should think like this. This is pi, this is sigma, this is positive. So it should show resonance as per the conjugation which I've shown you right here few minutes back. But what is going to happen right here? See, oxygen, it has formed 2 bonds with hydrogen, right? There is 1 lone pair on oxygen, there is 1 lone pair of oxygen, and this is 1 more bond. So people, 2 to 4 to 6 to 8. Can I say octet of oxygen is complete? If octet of oxygen is complete, its outermost configuration should be again 2s2, 2p6. Is there any empty orbital right here? No empty orbital right here. Yes. Correct? So no resonance at all, right? Because for the resonance, there should be pi, sigma, and empty orbital. Correct? 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 Yeah? Clear to everyone? Let me know in the chat box if it is clear so that I can give you a few more examples. Let me know in the chat box. Yeah? Okay? Because we know, I've told you a few minutes back. Since we are talking about pi, sigma, and empty orbital conjugation. Right? We are talking about this. But right here, no doubt you have pi, then you have sigma. But right here, there is no empty orbital. Pi, sigma, right here, there is no empty orbital. So no conjugation at all. Okay? Right. Let's talk about few more important things. Which will the molecule show resonance? Will the molecule show resonance? What about the first one? Will the first one show any sort of resonance? What do you think? Will the first one show any sort of resonance? Yes or no? Yeah, is it going to show resonance? What do you think? The first one I'm asking. See guys, understand like this. Which kind of conjugation we are talking about right here? Pi sigma empty orbital, right? That conjugation we are talking about right here. You can check it out. Have a look. See guys. First of all, P is forming 3 bonds with R. Correct? And right here one more bond. Correct? So is the octet of P complete? Octet of P is complete, absolutely. Octet of P is complete. Understand what I'll say. If the octet of P is complete, this one exception guys, okay? Except this is not the exception, this is a concept basically. The octet of P is complete first of all. We know octet of P is complete, right? But guys, if the octet of P is complete, its configuration should be 3s2, 3p6. Correct? This should be the configuration of this phosphorus after completing its octet, right? Since there will be 3d also with 0 electrons, right? Can I say there are empty d orbitals, right? So can I say I got the conjugation as pi sigma empty orbital? This is going to show resonance. Yes. Let me know in the chat box if it's clear. Let me know fast. Yes. Got it? Wonderful. Okay, let me know in the second one. Will the second one show resonance? What do you think? Will the second one show resonance? People, this is organic. You need to be very careful with the things. With small things you need to be careful with. Will the second one show resonance? See guys, just check the octet of sulfur first. Sulfur is forming 3 bonds with R and 1 bond right here. So octet of sulfur is completed. After completing the octet, can I say configuration of sulfur is going to be 3s2, 3p6? Yes. But there'll be 3d also with 0 electrons in sulfur, right? So empty 3d orbitals are there. Can I say I got the conjugation as pi, sigma and empty orbital? Can I say it is going to show resonance? Absolutely, yeah. Yes. What about the last one? What about this one, guys? Will it show resonance? What do you think? Will the last one show resonance? What do you think? Will the last one show resonance? Well, I can see majority of the people are saying no. Why is that? See, nitrogen's octet is complete, right? 3 bonds with hydrogen and 1 bond with carbon. So its octet is complete. After completing the nitrogen is going to have the outermost configuration as 2s2, 2p6 after completing the octet. Yes, right? So it's not going to have any orbital, any empty orbital right here. No doubt, this was pi, this was sigma. It should have empty orbital, but it's not having any empty orbital. So it's not going to show any sort of hybridization, any sort of this resonance right here. Yes, exactly guys. All of you are perfectly correct. Wonderful. Right? Wonderful guys. Okay. 3 more examples, then we'll end today's discussion. Then see guys, this resonance effect is not over yet. I've just started the resonance. In today's session, I made you understand the actual concept of what this resonance is all about, okay? I didn't do the questions based on this concept. In the next session, which I'll be taking, we are going to do the part 2 of this resonance effect, which is going to be very, very, very important, okay? Right? Okay, let me know among these, which all will show resonance. What do you think? Let me know fast. What about the first one? Is the first one going to show any sort of resonance right here? Supriya, I'll be doing that soon. Just wait for that. Will the first one show resonance? Absolutely guys, first one will show resonance. See, pi, this is sigma. This is going to have empty d orbital, right? It's going to have phosphorus will have empty d orbital, right? So the first one is going to show resonance. What about the second one? Will the second one show resonance? People, use your brain, use your chemical bonding concepts. Chemical bonding plays a vital role right here in the GOC. Look here, guys. Look here. Understand what I'll say. Understand what I'll say. Which kind of hybridization this boron is showing right here? It is forming 3 sigma bonds, 1, 2, and 3. So it will be sp2 hybridized. Yes. What is the configuration of boron? Isn't it 2s2, 2p1? Outermost configuration I'm asking. Yeah. 2s2 like this, 2 electrons in s. And in p, there will be 1 electron like this, ground state. If I'll ask you about the excited state, 1 electron will go to the p. So excited state is going to be like this. 1 electron right here, 1 electron over here. Is this the excited state, right? This is the excited state. Now, which hybridization is involved? sp2. Can I say these 2 orbitals will undergo mixing, hybridization, and there'll be 1 p orbital left over here. So there will be the vacant p orbital, guys. There will be the vacant p orbital. So over here, you'll be having the vacant p orbital. So this is pi, this is sigma, this is vacant p orbital. So hybridization is going to happen right here. Yes. And if I ask you what is going to be the canonical structure of this one, see, this is one canonical structure, it's another canonical structure. Let's make that. Shift this double bond, right? You're going to shift this double bond. You are shifting this double bond from this carbon, so this carbon is going to get positive charge, so it's going to CH2 positive right here, correct? This is single bond, this is CH, this is your double bond. Now this is BH2 right here, correct? Yes, can I say that? Can I say that? And people, I hope you remember there will be, since there was a single bond, this was neutral, now there will be negative charge on this boron. Yes? Right? Right? Absolutely. Perfectly correct. Perfectly correct. Perfectly correct. So are these 2 going to be the resonating structures? Yeah, absolutely. Yes, Priya, since right here it didn't have any charge, right? It was a single bond. Now it is getting a double bond. So definitely it will be having negative charge. If it had the positive charge, then due to the double bond, that positive charge would have got neutralized. There would have been no negative charge right here, correct? But it was neutral first. So due to the formation of double bond, negative charge got placed right here on boron. Yes? Correct? Okay, what about the last one? Let me know about the last one, guys. I just want to see the last one, by means of which I'll get to know whether you got the concepts or not. Let me know about the last one. Will it show resonance? Yes? Absolutely, this will show resonance. And what is going to be your homework, guys? You are going to make all its canonical forms. You are going to make all its canonical forms. Okay, take a picture of that and do send me in the comment box or in my personal Telegram, personal Instagram, wherever you find me, do send me that. Okay, I'll be personally checking it one by one, right? Okay, this was the first type of conjugation, which is your pi, sigma, and empty orbital conjugation. This was the first type of conjugation, empty orbital conjugation. I mean, pi, sigma, empty orbital conjugation, wherein resonance can happen. Okay, this not done yet. There are other conjugations as well, which I'll be letting you know in the next session. Okay, not now, right? Well, people, with this, I think our today's discussion is over. Yes. So for the ones who joined us late, let me tell you, we have come up with the NEET 2021 crash course for you. In this, you'll be getting trained by the teachers of your choice. And after that, at the same time, your whole syllabus will be getting completed in your physics, chemistry, as well as biology, right? The test series, mock test, everything is included right here in this test series. In this crash course. And at the same time, there'll be some separate sessions regarding the tricks and tips by means of which you can solve the questions in lesser time. Yes, and people, at the same time, it's going to be a two-way learning interactive platform wherein you can ask your doubts anytime your master teachers. Yes. And in order to get enrolled in this, if you want me to train you personally in your chemistry for the upcoming NEET 2021, just click on the Vedantu app. After clicking on the Vedantu app, just click on the NEET crash course. After clicking on the NEET crash course, use the coupon code as WSCC if you want me to personally train you for the upcoming NEET 2021. And apart from that, you'll be getting the discount of 20% right here after using this WSCC coupon code right here. There is one more way by means of which you can get enrolled in this. Okay, you just need to click on the link which is there in the description box of the video. Click on that link. Okay, use the coupon code, get added, right? Right? Okay. All right. Well, talking about the NEET 2021 test series, guys, which we have started right here for the ones whose preparation is up to the mark, right? For you guys, we have started the test series, right? And in this test series, it's not going to be only the writing of the test. There will be the test paper discussions with it after every session over here. Okay? And in order to get this test series, there is one more link in the description box of the video. Click on that link, use the code WSCC and get the additional 20% off right here. Okay? This is for the ones. This is for the ones whose preparation will be up to the mark right now, who just want the mock tests, test papers, everything to get solved, right? Okay, so we will one more link is there in the description box of the video. That is for the Telegram. Do click on that link, get added to the Telegram group and stay update about the classes. And for the ones who have not liked the video yet, please do like the video, share and subscribe the channel at the same time so that everyone gets benefited out of these sessions, right? I hope everything is clear till here. Yes, I hope everything is clear till here. I'll see you guys again tomorrow at the same time, and tomorrow we are going to continue with this resonance effect right here. Okay, till then you guys take care. Bye bye. God bless you all. Love you all. Take care. Bye guys.